Good morning, everyone. Thank you for being here today. We'll discuss particle size distribution in C formulations and how different grinding techniques in C milling lines can achieve a stable monomodal PSD. So let's get started. Comparison of multimodal and monomodal PSD. Bead milling in C formulations can result in two types of particle size distributions, monomodal or multimodal, depending on the grinding dynamics. A monomodal distribution features a single clear peak indicating uniform grinding. This results from consistent particle size reduction across the volume, even energy distribution in the milling chamber, and effective stabilization that prevents reagglomeration. A multimodal distribution has overlapping peaks showing a range of particle sizes. This occurs due to uneven energy transfer, causing varied grinding rates, differences in component hardness or resistance, reagglomeration, which broadens the particle size distribution. On this slide, you can see some examples of charts comparing monomodal and multimodal PSD. The top row shows narrow and uniform PSD. The slide shoulders and tails indicate minor size variations commonly seen in high precision milling. The bottom row presents multimodal PSD charts, illustrating active ingredient mixtures with distinct particle size fractions. The last two charts show technical AI with broad distribution, likely due to technical grade batch blending of different particle sizes. Each type of PSD in a C formulation may significantly affect product performance and processing efficiency. Physical stability. Multimodal PSD reduces stability in AC formulations due to varying settling rates, complex particle interactions, and an increased risk of oswald ripening, while monomodal PSD enhances stability and ensures greater predictability. Rheological properties. Multimodal PSD complicates flow behavior of the formulation, increases viscosity fluctuations, and makes viscosity control more challenging, while monomodal PSD enables smoother processing and more predictable rheology. Application properties. A multimodal PSD causes inconsistent droplet formation during spraying and increases sensitivity to hard water and additives in tank mixing. Monomodal PSD ensures a uniform spray pattern and provides better robustness and stability across various tank conditions. In summary, a narrow monomodal PSD improves stability, handling, and application consistency, making it highly advantageous for SC formulations. Factors leading to multimodal PSD in SC formulations. Two key factor groups can cause a multimodal PSD in SC formulations: reagglomeration or poor dispersion, and differences in physical properties of AIs. Reagglomeration or poor dispersion. Improper milling parameters or formulation strategies can lead to particles reclustering driven by electrostatic or van der Waals forces, resulting in a broadened PSD. Insufficient stabilizers may allow particles to clump or settle unevenly. Variations in milling conditions like temperature, bead size, or agitation speed can lead to inconsistent grinding and a multimodal PSD. Overextended grinding time may overheat particles, increasing surface energy and the risk of reagglomeration. Differences in physical properties of AIs. Single active formulations may contain varying size fractions due to blended batches of technical grade material. Multi-active formulations often involve ingredients with distinct PSD, making uniform grinding very challenging. Differences in hardness and grindability between actives lead to uneven grinding rates, producing a range of particle sizes. On this slide, we see microphotographs of particles from an SC formulation. Photo 1 shows suspension with a narrow monomodal PSD achieved through effective grinding. In contrast, photos 2 and 3 show suspensions with reagglomerated or poorly dispersed particles, resulting in a multimodal PSD. Photo 4 shows how two active ingredients with different hardness and grindability produce different particle sizes during grinding. To address a multimodal particle size distribution, the first step is to examine the suspension under a microscope. This allows you to visually identify the nature of the issue, whether it's caused by reagglomeration, poor predispersion, or uneven milling. Once the cause is identified, you can take specific actions to address it. For example, if the issue is with the formulation, you may need to adjust dispersants, wetting agents, or stabilizers. If the issue is with the milling process, adjusting bead size, milling time, or rotor speed can help. In some cases, switching to a more suitable grinding method may be necessary. Grinding strategies. Grinding strategies involve selecting the most suitable grinding method, optimizing operating conditions, and adjusting formulation composition. Selecting most suitable grinding method. To address differences in the physical properties of active ingredients, two key grinding methods can be applied in the C formulation lines: the pre-dispersion scheme and the pre-grinding scheme. Each method is tailored to specific grinding strategies depending on the initial physical properties of the SC premix. On this slide, you can see the setups for both approaches. The first features a high shear pre-dispersion module, ideal for improving weighting and initial dispersion of actives. The second incorporates a pre-grinding module, designed to reduce particle size before fine grinding. Optimizing operation conditions. Cooling system maintains efficient cooling of the formulation throughout the entire process, including the homogenizer or pre-grinding mill, the vessel before fine grinding, and the bead mills for fine grinding. Tip speed maintains optimal speed for consistent grinding performance. Milling media in fine grinding mills. Bead loading, maintaining 70 to 80% of the grinding chamber volume for optimal efficiency. Bead size, starting with larger beads, 1.25 to 1.6 millimeter, and moving to smaller sizes, 0.8 to 1 millimeter, for finer control. Bead material, selecting ceramic beads, for example, zirconium oxide, for their hardness, durability, and stability in aggressive formulations. Agitator type, using a disc agitator for effective sharing and grinding, achieving fine particles and uniform dispersion. Residence time ensures sufficient grinding without overheating. Solids loading balances the mill load to avoid exceeding capacity and maintain consistency. Adjusting formulation composition. Rheology stabilizers. Addition rheology stabilizers after grinding to maintain final viscosity. Dispersants, optimizing dispersant selection for even particle distribution. Wetting of actives, ensuring complete wetting to prevent clumping or reagglomeration. pH adjustment, monitoring and adjusting pH for ingredient stability and compatibility. Now let's talk about predispersion SC line. This slide outlines the SC formulation grinding process, starting with the predispersion stage. Ideal when active ingredients share similar physical properties. The process begins with high shear predispersion using a rotor stator homogenizer. This step breaks agglomerates into well-wetted primary particles and ensures dispersants fully adsorb onto their surfaces, preparing the premix for efficient grinding. For a 2,500-liter batch, up to 10 cycles, approximately 25,000 liters of premix is circulated over 1 to 2 hours through the homogenizer. A capacity of 25 cubic meter per hour and integrated heat exchanger provide the necessary throughput while maintaining controlled temperatures during circulation. Key parameters and equipment. Temperature control. The heat exchanger of the homogenizer ensures circulation temperatures stay below 25 to 30 degrees. Then the cooler of the premix vessel reduces the premix temperature to 20-25 degrees before sending the batch to milling to ensure smooth grinding in the next phase. Both bead mills feature an efficient cooling system that maintains the formulation temperature within the mills at 20-25 degrees. Circulation through homogenizer before further grinding. It requires 6 to 10 cycles for complete dispersion. Homogenizer handles 25 cubic meter per hour for efficient agglomerates breakdown. Feeding pump supports viscosities up to 2000 centipoise. This homogenization process deagglomerates particle clusters without milling the primary particles. Selecting the right dispersant package is critical for optimal results. Milling sequence and target PSD. After predispersion, the PSD should have a D90 value between 40 to 70 microns. For the main milling stage, the goal is to reduce this further to a D90 of 5 to 10 microns. A linear setup where the output flows from one mill to the next is ideal. Typically, 2 horizontal agitator bead mills are used in succession. The first mill, loaded with larger beads, around 1.5 millimeter, initiates particle size reduction. The second mill, with smaller beads, approximately 0.8 millimeter, refines the particle sizes to achieve the desired PSD. Both bead mills are effectively cooled. For a batch size of 2.5 cubic meter, the recommended setup is the Netsch horizontal intensive grinding system, Discus 150, featuring a 150-liter grinding chamber and powerful 75 to 90 kilowatt drive, offering high grinding efficiency, effective cooling, and continuous processing. This slide presents data on various size models of the Discus horizontal intensive grinding system, offering typical throughput ranging from 20 to 2500 kilograms per hour and batch capacities from 10 to 2500 liters. A small-scale LabStar model is available for laboratory use. Pre-grinding a C line. Achieving a model PSD can be challenging when working with single active ingredients of varying sizes or multiple actives with distinct PSD. For example, in formulations where one active has particles around 200 to 300 microns and another under 100 microns, high energy coarse pre-grinding is essential. The use of coarse pre-grinding significantly enhances efficiency compared to predispersing techniques. As you can see in the scheme of the pre-grinding line, a pre-grinding module replaced the high-share predispersing module in predispersion line. Coarse pre-grinding is performed by circulating the formulation through a specially designed high-throughput bead mill before proceeding to fine grinding. The number of circulation cycles needed to proper pre-grinding depends on the initial physical properties of the active ingredients in the formulation. Efficient cooling of the pre-grinding module is essential to ensure optimal performance. During this process, larger beads are employed to efficiently decrease the size of larger particles, such as those in the 200 to 300 micron range, while smaller particles below 100 microns remained unaffected. At the outset, the PSD yet exhibits a multimodal nature, but coarse pre-milling transforms it into a more continuous distribution, shifted towards smaller particle sizes. For such scenarios, a high-throughput bead mill serves as a better alternative to a homogenizer. This equipment effectively disintegrates large particles and breaks down agglomerates, resulting in a more consistent dispersion ready for the further fine grinding. In the final stage, finer beads are used for additional refinement, further narrowing the PSD to achieve the desired monomodal distribution. The efficient pre-grinding process is powered by the Netsch Profi pre-grinding mill, a disc agitator bead mill uniquely adapted for high throughput coarse grinding. Operating at a peripheral speed of 8 to 12 meters per second, the Profi 20 model processes up to 25 cubic meters per hour with 2 to 4 millimeter grinding beads. The Profi 20 is built for demanding large-scale pre-grinding tasks. It delivers 30 kilowatt of power with a flow rate between 10 and 25 cubic meters per hour, using a grinding chamber volume of 20 liters. It's capable of handling batch sizes up to 6 cubic meters, making it ideal for high-volume operations. As you can see in the chart, the Profi mill requires less energy, achieves faster results, and reaches smaller particle sizes compared to a rotor starter high-share homogenizer. In conclusion, achieving a monomodal particle size distribution is critical for stable high-performance SC formulation. This outcome is achieved through two essential grinding techniques: pre-dispersion and pre-grinding. Pre-dispersion is ideal for active ingredients with similar physical properties. It breaks down particle clusters, ensures even wetting, and prevents reagglomeration, preparing the premix for final fine grinding. Pre-grinding is essential for formulations with active ingredients that vary in hardness, grindability, or size. It involves coarse pre-milling to break down larger particles, making them more uniform and better prepared for final fine milling, which is especially important in multi-active formulations. With advanced equipment like Netsch, Profi, and Discus mills, these techniques ensure stable neuro-PSD. Profi mills handle pre-grinding, while Discus mills achieve fine grinding, optimizing performance, stability, and reliability in SC formulations. Thank you, and your questions, please.